Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. How's everybody doing today? Good, good. Great, good. Yeah, hopefully everyone's had a more productive day than me, because it's tough on the day after the election. So, I keep telling myself that I need to close the electoral map, but I keep kind of going back to it. So, it's tough. I know it's a big election too. Okay, but I did get something done this morning. Yeah, it's close. So I finally finished the project specs, and I also put up the starter code for the final project. So we're going to spend the first 10-15 minutes today talking about that. Okay. I also want to walk you through to how you install this PDE toolbox within MATLAB too, because you're going to need that for the project as well. Yeah. Oh, nice. Dang, 3 screens. That's nice. And then after we do that, we're going to continue on with our lecture notes on 2D finite elements. Okay? So today we're going to finish up the first set of lecture notes on 2D heat conduction, and then probably we'll have time to start the second set of lecture notes, which is on isoparametric elements. And both of these lecture notes, especially the isoparametric elements one, that's going to be really key for your project. So that's definitely kind of the biggest influencer for that. Okay. But before we do that, are there any questions I can answer just about anything in the class?
Will we get a homework assignment before the next midterm?
Yes. I'm gonna be working on that tomorrow. So the next homework assignment is going to be on the 2D stuff that we're going to be covering soon. So.
And when would that be due?
Just probably it's going to be due the Monday before the midterm, and so I'll probably have it due then. And I'll post the solutions basically right after it's due as well, just so you'll have that for the as a reference for the exam. Yeah.
Thank you.
Mm-hmm. Yeah. Any other questions? So the question is, it's about the current topics being discussed, right? And not the answers. That's correct. So the midterm is going to be on basically the strong form, weak form, finite element form. All the stuff we did in 1D for homework 3, and then I'm also going to give one more homework 4, which is going to be on the 2D stuff. So the stuff we're going to cover, over the next couple lecture sessions. Okay. Okay. Any other questions? Looks like my iPad disconnected, but that's okay. So I'm going to share my screen on my desktop. So let's talk about the project. Okay. And so this is the project spec. So I uploaded this onto Canvas already. So you should be able to view it. So there's if you look into the files section on Canvas, you should see a new folder there called project. So I have the specs here, and I also have all the starter codes. So you should see 3 ones for part 1, part 2, and part 3. Okay. And so just like I mentioned on Monday, your final project is to basically write a code to solve the 2D heat equation on an arbitrary finite element mesh. Okay. And so here, on the left right here, I'm showing you the mesh. And so basically our geometry is kind of made up of these 3 squares. And so we have kind of a backwards L geometry. And then what you're going to do is you're going to implement the code to basically compute the element stiffness matrices, compute the element forcing vectors, assemble, apply boundary conditions, and all that. And then once you solve, you're able to get kind of a temperature field that looks like this. Okay. And so I think this is the result after part 3. So after you've implemented basically everything in the code, you get a result that looks like this. So you have a plate that's hot over here, shown in the red, and then in the blue, you have parts that are cold and kind of everything in between there. Okay. And so the biggest part of this project is the fact that every element that you have here is going to have a different. They're all going to be triangles, so at least you'll have that going for you. But they're all going to be arbitrarily oriented, right? So they're all going to be slightly different sizes, and their coordinates are all going to be different. And so what's going to be key in this project is going to be the the topic that we're going to start going over today, which is this idea of an isoparametric element. Okay. And so I don't want to get into too many details right now, because that's going to be the subject later. But basically, with an isoparametric element, you're going to go from the domain here in physical space, which I have over here. So this is what you would have in the mesh. And so you can imagine, this is an arbitrary triangle that you have. And then what you're going to do is you're going to transform that into what's called the parent space, or the parametric space, which is the triangle that always kind of looks the same. Okay. And so you can think of this as kind of like the change of variables that we did in 1D when we did our Gauss Quadrature. So this is kind of the 2D version. And so that's going to be a big subject of what we cover over the next couple lectures. Okay. And so before you begin, there's an extra package that you need to install in your MATLAB. So I basically covered this how you install that here. So basically, in your MATLAB window, if you open up kind of your general one here, okay, at the top of your MATLAB window, you should have this tab up here called Apps. Okay, and so once you click that, you can click on this button right here to say Get More Apps. Okay, and then once you do that, it's going to open up a new window. And then from here, it's almost like kind of like the iTunes store, but for MATLAB. So it's kind of funny how everyone kind of has the same structure for that now. And so in here, you're going to search in the search bar. And so the toolbox that we want is called the Partial Differential Equation Toolbox. And so the short for this is just PDE. So if you search PDE in the search bar, it should be the first toolbox that you come across. So you're going to click Partial Differential Equation Toolbox. And so I already have mine installed, but once you click this, there should be a button here for you to install. Okay, and so that's the first thing that you should do, because that's going to give us access to functions that will allow us to mesh the geometry, and also to in order to get some information about the mesh. Okay. Okay. And so since we're doing the 2D heat equation, here's the equation that we want to solve. So it's just k times the Laplacian of t, and so that's partial squared t partial x squared, plus partial squared t partial y squared, plus the thermal generation term is equal to 0. And in this problem, starting with part 2 onwards, you're going to have a thermal generation term, and that's going to be given by this. Okay. All right, question. Nice. Okay. And so what I've done basically is that it's the code for this is it's going to be pretty long. So I'm going to warn you guys right now. It's a decent amount of coding. I've written most of the structure of the code for you already. So the main parts that I've left you to do are kind of the main parts for the finite element method that we're going to go over in the class. But all of the kind of like the infrastructure for the code and all of the variable setup, I've already kind of done that for you. But it is a lot. And so what I've done to kind of help you along is that I've split the project into kind of 3 parts. Okay, and so in the first part of the project, what you're going to implement is basically a finite element code that solves the diffusion equation with Dirichlet boundary conditions. Okay, and so what that means is that for part 1, we're not going to consider any thermal generation. So we're going to set s of x and y is equal to 0. And the only boundary conditions that we're going to specify is Dirichlet, because Dirichlet is a little bit easier to handle, because we've done that kind of a million times at this point. Okay. Okay. And so in this part of the specs, I kind of walk you through the starter code, which I have kind of right here. Okay. And I tell you what each of the variables mean and what each of these lines mean. Okay. And then I go over basically what you need to implement. And so the main things that you need to implement in this part is 1, the code to implement the the computation of the element stiffness matrices. 2, the implementation of the assembly. And so once you have all the element stiffness matrices, you can assemble them into the global linear system. And then 3, you need to implement the how to specify the Dirichlet boundary conditions. And then from there, then you can solve. So all the same steps that we've seen before, for these kinds of MATLAB codes, except for in 2D, things are going to be a bit more complex. Okay. And so one thing that I did want to go over with you before, as a group, is to basically, how we actually specify these boundary conditions. Okay. And so if you run your starter code, you should see one of the figures. I think it's figure 2, that gets produced like this. Okay. And so what you have in this figure is you have your geometry. Right? So remember, we have our L geometry, backwards L. Okay? But you can see here what MATLAB has done is it's tagged all the sides or all the edges for the geometry. Okay? And so we have E1, and so that stands for edge 1, and then edge 2 is up here, I believe. I think it's covered with it. They have edge 3, 4, 5, 6, 7, 8, 9, and 10. And so these are important because these are going to allow us to specify the boundary conditions. Okay? So if you kind of think back to our frame code, remember the way that we specified boundary conditions was we had to specify 2 things. We had to specify 1, the location for the node, or the degree of freedom where we want to specify our boundary condition. Okay? And 2, we're going to specify the value. Okay? And so the way that manifests in this code is that the location that we want to specify the boundary conditions is we have to specify it on the specific edge. Okay? And so what you'll see when you open up the code is that there will be two vectors that you need to assign. So the first one is called Dirichlet edges, okay? And that in that vector you specify the index for all the edges that you want to specify the boundary conditions on. And then the other vector is this Dirichlet values vector. So that defines, you know, what value that you want to put on this. So the structure again is very similar to how we did our frame code. Okay. All right, question. So the question is that, so like T at E1, E2, et cetera, equals 100 if constant temp. Yep, that's exactly right. Yeah, so basically what you're going to set is that if you want to set like E1 to have a temperature of 100, what you're going to do is in the Dirichlet edges vector, you're going to say that, you know, you want to specify boundary condition on edge 1. And then in the Dirichlet values vector, you're going to specify, you know, a temperature of 100. So that's basically the structure for that. But if you kind of refer back to our frame code, you know, this structure should hopefully be familiar to you guys. Okay? And that's kind of why we wrote that the way that we did back then. Okay. All right. And so from there, I kind of described the other you know, data structures. Okay. You know, we're going to talk about Gauss Quadrature a bit today. Okay. And then this describes to you what you need to actually implement, which is the element stiffness matrices, assembly, and the Dirichlet boundary conditions. Okay. And so, you know, the reason I kind of grouped all this together in part one is because, you know, by the end of part one, you know, you should have a code that can run kind of a basic finite element simulation. So it's not going to be everything because it's not going to include the thermal generation or the Neumann boundary conditions, but it at least will give you something that you can check. Okay. And the nice thing about this this package that we're using is that it gives you a way to kind of check your results as well, okay? And so at the bottom of this code, what you should see is that I've already implemented kind of what I call like a reference solution, okay? And so what I've done basically is I've set up a way for basically MATLAB to compute what the correct solution is for this, okay? And so when you run this code, it'll produce, well, it'll produce 6 figures, but the 5th figure will be the solution that you computed. So that's the result from your code. And then figure 6 will be like the reference solution or the true solution, okay? And so ideally, when you're running your code, figure 5 and figure 6 should be the same, okay? If you implemented your code correctly. But if they're not, then that gives you a hint that, you know, you need to go back and kind of check something in your code, okay? And so, you know, I set this up like this just so that, you know, you have something that's kind of built into the code to kind of tell you whether you're right or you're wrong, okay? Okay. And this is going to be implemented in all 3 parts, okay? And so, you know, I have this note here so that you don't change this, and that's important, because if you change the reference solution, then it's you're going to be kind of going down a wrong path. Right? Okay, are there any questions so far on part 1, or just the project in general? Okay. Right, so that's part 1. So part 1 is just going to be, you know, just the element stiffness matrices, the assembly, and the Dirichlet boundary conditions. So that's kind of the minimum requirements to do a project, okay? Or to do a finite element code. So you're going to have to do all 3 parts, but you know that's yeah, at least by the end of part 1, you should have a code that works. Okay? And so in parts 2 and 3, we're going to start to introduce some more complexity and some more flexibility. Okay. And so in part 2, what you're going to implement is the thermal generation. Okay? And so you're going to modify your code, or you're going to add some additional code to basically, you know, compute the contributions from the thermal generation function, you know, which I have given here. Okay? And we'll go over the algorithm and how you do this, you know, later on in the notes. Okay? Right? And so that's part 2. And then part 3, you're going to implement the Neumann boundary conditions. Okay? And so I saved this one for last because the Neumann boundary conditions are actually probably the most complex part of this. And the real difficulty with that just has to do with the fact that, you know, we don't know how our elements are going to be shaped beforehand. Okay, and the thing is with Neumann boundary conditions in 2D, what we actually have to integrate is a line integral, right? And so the most difficult part of the Neumann boundary conditions is determining, you know, which edge in your triangle is actually on the boundary. Okay, so there's an algorithm that I've kind of developed in there for you, and I've kind of walked you through step by step. But that's going to be the most difficult part, because when you're evaluating the Neumann boundary conditions, you don't want to integrate over the wrong edge and add contributions to the wrong nodes, because otherwise you're going to get a very wrong solution. Okay, and so, you know, when you get to part 3 of the project, make sure you really pay attention to that part, and you're really, you know, integrating over the right places. Okay. Okay. And so the other thing that changes, and we'll go over this later, is that the Gauss points actually change on your triangle too, because it's not in the standard domain. So I've given you here the Gauss points for this triangle that you're going to implement for this 1D integral. Okay. Okay. And so those are the three parts of the problem. So the they kind of represent all the setup for a finite element problem that we've been going over in the class. So element stiffness matrix, thermal generation term, Neumann boundary conditions, assembly, Dirichlet boundary conditions itself. Okay, and so all those are kind of split up between the parts. But in this project, I'm also giving you a chance to get some extra credit. Okay, and so that's why I call this part bonus. So this part's not required. So if I'm not going to be providing you starter code for this because it's the code organization is actually a big part of this, but what I want you to do in the bonus part is to basically make this code a lot more efficient, okay? Because the starter code that I've given you, I've kind of broken it up in a way such that it's kind of systematic on how you implement things, but it's actually not the most efficient way to implement a finite element code. So actually, you can actually improve both the speed and the memory that it takes up, pretty significantly if you make some changes, okay? And so I described here what those changes, would be, or at least the changes that I would make. But again, this part's not required because this is not a class on coding or how to make your code more efficient. So this is just it's going to be a small part of extra credit. So I said I think here I said if you do this part successfully, it'll be worth 10 points extra credit, but that's going to be out of 200 points. So it's going to be a very small percentage. But for those of you who are interested, this part right here will give you a pretty good glimpse of how these finite element codes are actually implemented in practice. Because the algorithm that we're going to be solving, that we're going to be using for this in the starter code, it works, but it's not as efficient as what's under the hood in ANSYS or something like that. So this bonus will give you kind of a look in, or at least give you a try at implementing these finite element codes exactly how the commercial codes do it. Okay, but again, it's optional, so you don't have to do this part. Okay, and so here what I have at the end is basically just a summary of all the things that I expect you to implement and what part that you can find. Okay, all right. Any questions on this so far? Okay. Okay, so let's talk deliverables. So what you're going to turn in at the end of this project is actually going to be mostly a report. Okay. And so, of course, I'm going to ask you to submit your codes for this project. So there should be 3 of them. But the other thing that I want you to write up is a final report that basically summarizes your findings. Okay. And so in your final report, there are certain things that I'm going to expect you to have. Okay. And so, what I have listed here are some figures or some plots that I expect you to have. Okay. And so first of all, I want you to show a plot that shows me that the answers that you get at part 1 matches up with the reference solution. Okay. And so I want you to do the same for part 2 and part 3. Okay, so these are just figures just to show me that your code works, and these are the figures that I get out of it. Okay. In part 4 of this code, what I want you to do is what's called a mesh convergence test. Okay, and so what I mean by that is I want you to run your code at different mesh densities. Okay, and so you're going to change the size of the mesh, and then you're going to run your results and see how your results change as a result of your mesh change. And so we'll discuss this more kind of after the Thanksgiving break, but all this is basically is you're going to run your code just for different mesh sizes and then just kind of report on the results. Okay. Yeah. Hopefully, hopefully this kind of gives you a good look into how these codes are implemented. Okay. And so the 5th plot that I want you to do is I want you to basically take your code and change the boundary conditions a bit. And see how that affects your results. Okay, so kind of the same thing that we've done with kind of our frame code. So just kind of change it up a bit, and just to make sure that your results match up with under different conditions. Okay? And then I also want you to compare your results with ANSYS. Okay, and so because this is kind of a relatively simple 2D case that we're doing, you can set this up in ANSYS pretty easily too. So if you kind of follow the same algorithm or the same process that we did in ANSYS activity 1. You can set it up in exactly the same way, okay? And so ideally what you should get is that the results from your MATLAB code and also in ANSYS should get the same results, okay? And that's what I want you to do here. And then the 7th plot, if you choose to do the bonus part, I just want you to show your results from that too, okay? And so in total, the deliverables that you need are going to be the final report, which is going to be as a single PDF, and all your MATLAB codes. Okay? And then the due date for this, which is it's at the top of these specs, is going to be Monday, December 21st. Okay, and so that's going to be the Monday after finals week. So that again, just to make sure that you guys have enough time to do your finals and write up your report in the end, but it also gives me enough time to grade it and submit the grades by the. Okay. And so the next section for the specs is the final report component. So these are all the sections that I expect you to have in your report, and kind of what I'm expecting for each section. And so the structure of the final report kind of follows the same format as like a scientific paper or like a journal publication. Okay. And so first, I want you to write an introduction. Then I want you to describe your methodology. Then I want you to show your results. So in your results section, that's going to include all the figures that we just talked about. And then just some comments on conclusion. Okay, and so the big thing that I'm going to look at your report for your report is like, yes, I'm going to look at your plots just to make sure that they match up, but I'm also going to be looking very closely at the methodology section. Okay, and so the methodology section, what I want you to describe is basically the theory and the equations that went into developing your code. Okay, and so what I want you to keep in mind for this section is that the person reading your report. Well, first of all, it's going to be me, obviously, but then what I want you guys to also write for is, if you want to, if you were to give this report to like a fellow peer, like a fellow graduate student that you have here at Cal State Fullerton, who maybe hasn't taken a finite element class, but they're interested in reading your report just to see that, what kinds of things did you learn in finite elements. I want you to write this methodology section as a way to kind of teach them, the theory and the equations that you learned in finite elements. Okay, and so it's. For this methodology section, I'm kind of putting the teacher's hat on your shoulders. So, if you were to kind of, write up a documentation or write up a way to kind of teach someone about finite elements, through, what you did for this project here, that's kind of the mindset that I want you to have for this methodology. Okay, and so write your methodology as if you were to teach someone. So, I really want you to be kind of detailed with the methodology and kind of be, I want you to kind of develop the theory. So you don't have to go through the proofs or, be as detailed as we are in the lecture notes, but I should be able to follow your thought process and follow the methodology and kind of say, if I was kind of a novice at finite elements, but I still had some background in engineering, I would be able to kind of understand what you're doing. Okay. And so I'm really going to be paying attention to this section pretty closely. So make sure that you're, that you're writing it, writing it well. Okay. Okay. And so let's discuss teams or the lack thereof. So this is going to be an individual project. So I want everyone to develop the code and write the report. Okay. But that said, I am encouraging you to work together with your classmates because it's going to be a lot of code development, and it's going to be using your classmates as a resource as people who are also writing the same code is going to be really valuable for this. Okay. But I will say that when I say work together with your classmates on the code, that doesn't mean that one person. That doesn't mean that just one person works on the code and everyone else has pom poms just cheering them on. Okay. When I say work together, I mean everyone's working together on the code, and you're just kind of bouncing ideas off each other, and you're kind of simultaneously developing the code in parallel. Okay. So don't copy each other's code because that's very obvious. That's very obvious for me to see. But definitely discuss with your classmates and discuss with your peers and kind of bounce ideas off each other because it's only going to help. Okay. And of course, I'm going to be a resource as well for these for this project too. So when if you're having trouble developing the code, definitely reach out. Okay. All right. And so I know that this project it's going to be a lot of work. It's going to be a lot of first it's going to be a lot of coding and it's going to be a lot of writing too. But I want this to be something that you guys are going to be proud of. Okay? Because finite elements, as you guys know, after reading a lot of your introduction emails, it's a skill that a lot of people find really valuable, especially in the professional space. Okay. And so with this final project, I want this to be something that you can basically use it and show that, say, I really understand finite elements. I understand the theory, I understand the implementation, and I can do basically any kind of finite element work that you can ask me to do. Okay. Because that's the goal. That's my goal for this class. That I want everyone to leave here, feeling like they're an expert in finite elements, and that they can come into a company and be inserted into a finite element role, and kind of I want you guys to feel comfortable that you can contribute in day one. Okay, and this project kind of goes. That's kind of the the motivations behind that. Okay. Okay. Any questions about the final project or the report or anything? Okay. Right. So all the starter code and the specs are there for you online right now. So definitely download them. You know, if you just so you can take a look. Right. But if there's no more questions, I think we're going to go ahead and continue on with our regularly scheduled lecture. Okay. So let me kind of rejoin here. My iPad has been Zoom on my iPad has been crashing a lot recently. Not sure why. Okay. Right. So we're basically gonna pick up where we left off on the last set of lecture notes, which is you know, rectangular elements. Okay. And so last time what we covered was kind of the basics of finite elements in 2D. Okay. And specifically the heat equation. Okay. And so in particular, what we saw was, you know, if we had a triangular element, you know, how do we go about solving this? Okay? And so what we found for this was we saw its shape functions. Okay? And we also saw its element stiffness matrix. Okay? And we also saw how to compute these. Okay. And so I think that's kind of the last thing that we did was we did an example on how to compute that. Okay. And so I think you know, where we left off was this idea of a 4-node triangle or 4-node rectangle. Sorry. Okay. And so what we said was that the interpolation function for this rectangle, okay, looks like the following. So we had t of x and y is equal to a0 plus a1x plus a2y plus a3xy. Okay. Okay. Because remember, the everything that we're going over, you know, for these 2D elements has linear shape functions. Okay. Because linear terms are nice because they're easy to evaluate. Okay. But with the 4-node rectangle, the fact that we have 4 nodes here, so 1, 2, 3, 4. Okay. And so, you know, when we have 4 nodes, we have, you know, one too many nodes that we can you know, use for our interpolation function. Okay. Because with 4 nodes, that means that we have to have 4 unknown coefficients. Okay. And so after we've done the constant term, we did the x term, we did the y term, right? We need to include one more term. And so that one more term that we include is this a3xy. And so technically it's not a linear term because it's, you know, we have an x and a y multiplied by each other, but it's also technically not a quadratic term because it's not, we don't have x squared or y squared or anything like that. So it's a mixed term. Okay. And so, you know, this might seem like a relatively harmless term right here, but you can see it, but you will see later that it actually, you know, it's actually going to complicate things quite a bit. Okay. Okay. And so at this point, you know, we're going to proceed, you know, in the same way that we did last time, is that we need to solve for the coefficients a0, a1, a2, and a3. Okay. And remember, the way that we're going to do this is we're going to force the element interpolation function to equal the nodal values. Okay. Okay. Because remember, at each node in this triangle, we're going to have a solution for our temperature. Okay? And so we're going to have T1, T2, T3, and T4. Okay? And then also at each of these nodes, we're going to have their coordinates, right? So at 1, we're going to have x1, comma y1. Okay? And then at node 2, we're going to have x2, comma y2. Okay? And node 3, we have x3, comma y3. And then node 4 is going to be x4, comma y4. Okay? And so when the spatial coordinates equal these nodal values, then they have to have the nodal solution. Okay? And so when we do that at all 4 nodes, we're going to have a system of 4 equations and 4 unknowns. Okay? And so again, I'm not going to solve this a system here because it's it's going to take a long time. But you can imagine, you can solve that system because it's simply just going to be a linear system for A0, A1, A2, and A3. Okay. Okay. Any questions on this so far? Okay. Okay, and so we can plug all that in, and then we can get the following. We can express the interpolation function in the following form. Okay, and so basically, after we solve for A0, A1, A2, and A3, we get that T of x and y, okay, is equal to T1 N1 plus T2 N2 plus T3 N3 plus T4 N4. Okay. And remember these n's right here, these are our shape functions. Okay. Right. And so these are going to be functions of x and y, and they're going to take a different form compared to our shape functions for the triangle. Okay. And so let me write these out. And so this is going to be n1 of x and y. And so this is going to be x minus x2 times y minus y2 all over x1 minus x2. Okay. Times y1 minus y2. Okay. Okay. So that's n1. So let's write out n2. And so n2 is going to be x minus x1 times y minus y2. And it's all divided by x2 minus x1 times y1 minus y2. Right, now we have n3 of x and y, and so this is x minus x1 times y minus y1 all over x2 minus x1 times y2 minus y1. Right, and finally we have n4 of x and y. This is going to be equal to x minus x2 times y minus y1 all over x1 minus x2 times y2 minus y1. Okay. Okay. And I should mention that for this problem, we're going to basically assume that our domain is has straight edges. Okay. Because you'll notice in these equations here, I don't have x3 or x4 in there, right? And so our domain actually looks like this. And so again, we have 1, 2, 3, 4. Okay. And this is going to have coordinates x1, y1. Okay. And this is going to be x2, y1. And it's going to be x2, y2. Okay. And this is x1, y2. Okay. And so basically what this assumes is that node number 4 is going to be right on top of node 1, and node number 3 is right on top of node 2, and then node 1 and node 2 and node 3 and node 4 are kind of horizontally, across each other. Okay? And so this isn't the most generic quadrilateral, but just it kind of helps to make the calculations here a bit simpler. Okay. Okay. So any questions on the shape functions for the 4-node rectangle? Okay. Okay. And so another thing that we're going to need in order to compute the element stiffness matrix is going to be the shape function derivatives. Okay. And so basically we're going to take the derivatives of each of the shape functions in both x and y. And so first let's take partial n1, partial x. And so this can be y minus y2 all over the area. Okay. And so you'll notice in the denominator we have basically x2 minus x1 times y2 minus y1. So that's just going to be simply the area. Okay. And similarly, we can take a partial n1, partial y, and we get x minus x2 all divided by a. Okay. Then we have partial n2, partial x. This can be y2 minus y all over a. Okay. Then we have partial n2, partial y. And so this is going to be x1 minus x all over a. Okay. Then partial n3, partial x. So this is going to be y minus y1 all over a. And then partial n3, partial y. And so this is going to be x minus x1 all over a. Okay. And finally, we have the quantities for n4. Okay. And so we have partial n4, partial x. And so this is going to be y1 minus y all over a. Okay. Then we have partial n4, partial y. And it's going to be x2 minus x all over a. Okay. And so these are all the shape function derivatives that we need. Okay. And so basically what we can use these shape function derivatives to compute the gradient of w and t. Okay. Because remember, the way that we computed our element stiffness matrix in 2D problems, we had to evaluate basically this integral like this. Okay. Okay. And so this integral right here became our element stiffness matrix. Okay. And so we can use these variables here, or these shape function derivatives, to compute them. Okay. And so I'm going to write out the expression for delta t. Right. So delta t, the way that you can compute this is the multiplication of these two matrices. Okay. And so it's going to be partial n1 partial x, okay? Partial n2 partial x, partial n3 partial x, partial n4 partial x, then partial n1 partial y, partial n2 partial y, partial n3 partial y, partial n4 partial y. And this is going to be multiplied by a vector of our nodal temperatures. Okay, so it's going to be T1, T2, T3, T4. Okay. And so we can get a similar expression for our del W, so the gradient of W. Okay. And then once we get these expressions, we can plug them into here. Okay. Okay. And then once we do that, we can perform the matrix-matrix multiplication. And then what we're going to get from that is a 4x4 element stiffness matrix. Okay. Right. So this is bigger than our element stiffness matrix for the triangle, right? Because for the triangle we only had 3 nodes, and so our element stiffness matrix was only 3x3. But since we have a 4th node for the rectangle, you know, that's going to increase the size of our matrix to a 4x4. Okay. Okay. Any questions on this? Okay. Oh, sorry, Stephen. I just noticed your question here. So the question is, as far as time frame is concerned, how long do you quote for this project, considering the person is already knowledgeable about the theory and the concepts behind? Yeah. So the you mean the time frame to how long to complete the project? Yeah. So the I would say, you know, I would definitely start working on this. You know, you're not going to have enough theory to start the project today, but after the lecture on Monday, you know, you should have enough to at least get started on part 1. So I would kind of get rolling with that kind of right away for that. Yeah. And so I would kind of work on this, you know, a little bit every week, just because as we kind of introduce a theory, then you can implement it to. Oh yeah, yeah. You should definitely start working on it. Basically, starting on after the lecture on Monday, you should be able to start working on it, and then, you know, we can start that discussion, and, you know, I can kind of help you out with the codes. Yeah. Mm-hmm. Yeah. Yeah. Sorry about that. I somehow my Zoom window didn't flash once you had your question, so I just noticed it now. Mm-hmm. Okay. Are there any other questions on this page right here? Okay. And so, you know, performing the this you know, computing this element stiffness matrix, you know, it's going to be different than what we did for the triangles, right? Because remember, you know, the triangles we could the element stiffness matrix for the triangles we could actually compute by hand, because our shape function derivatives here, you know, if you remember from the triangle, those were all constants, and so there was no x or y in there at all. Okay. But because of the rectangle, so remember the rectangle had this additional cross term, and so we had this xy cross term, right? And so because of that term, you know, when we compute these shape function derivatives, we still have a y, we still have an x kind of floating around here. Okay? And then when we perform this matrix multiplication, you know, the problem is going to exacerbate. So we're going to have, you know, y squared and xy and x squared, you know, and stuff like that. And so performing this integral here for 16 terms, you know, it's you know, you're very quickly you're going to realize that this is just not feasible to do by hand. And don't worry, I'm not going to make you do any of these by hand either. At least not by the analytical integral. Okay. And so, you know, the question kind of gets asked is, you know, can we make this step easier? Because, you know, we're going to have to perform this integral, and to have to do it 16 times is really kind of unreasonable to do. And luckily, the answer is yes. Okay. And we're going to bring back an old friend. Maybe not that old, but, you know, we went over a couple weeks ago, called Gauss Quadrature. Okay. So remember, we went over Gauss Quadrature in the 1D case as a way to kind of evaluate integrals without actually integrating. And for the 1D case, it was kind of useless because integrating in 1D is not that big a deal. But in 2D, you can see you'll see is that it's going to save you a lot of work. Okay, and so let's get started. Okay, right. So the idea with Gauss Quadrature is to perform integrals or to compute integrals without taking the antiderivative. Okay. And so formulaically, it looks like this in 2D. Okay. And so let's say that we have a double integral. Okay. And so we have double integral from -1 to 1. Okay. And that's going to be important because that's Gauss Quadrature only works for certain integration bounds. Okay. And say we have a function f of x and y. We integrate it over dx dy. Okay. And so instead of actually performing that integral, what we can do instead is we can do a summation, a weighted sum of the function of the integrand evaluated at very specific points. Okay. And so this right here is a weighted sum. Okay. And so this is actually really helpful because usually the difficult part and kind of the annoying part with doing integrals is actually this antiderivative part right here. Okay. Because the integrand you actually already have, right? And so if we kind of think back to the project, I gave you the integrand for the thermal generation to be x squared or 10,000 x squared sine of y pi. Okay? And so if you wanted to integrate that, you could, and actually that one's not that bad. But for other more complex functions, it gets to be more complicated. So a lot of times it's easier, especially easier to program. Just a simple summation like this. Okay. Okay. And so just like we saw, just like in the 1D, we have different ways that we can produce the quadrature. Right? And so the different ways are going to be defined by how many points that we use. Okay? She ate already. Don't feed her. Okay. And so there's lots of different rules here. Okay. And you can't just choose an arbitrary number of points. So you can't just say I want to do a 3-point rule. So for a 2D rectangle like this, there's a 1-point rule actually. And so this is the simplest one that you can do. Okay. And so the 1-point rule basically says this. Okay. Okay. And so if we have the integral from -1 to 1 and the integral of -1 to 1, okay, of f of x and y dx dy. And so the 1-point rule basically says that we can approximate this integral. And so I'll do a little squiggly equal sign. Okay, to indicate this is approximately. This is approximately equal to 4 times the integrand evaluated at 0, 0. Okay. All right. And so, the 1-point rule is very simple. So all you have to do is just take the integrand, evaluate it at 0, 0, and then just multiply by 4. And then that's a 1-point Gauss Quadrature. Okay. And so even though this is technically a Gauss Quadrature, it's not very accurate because it's kind of the simplest way to do it. And so, this is kind of convenient, but a lot of times this doesn't give you enough accuracy, especially if you want to do a finite element. Okay. And so what's more common for finite elements is actually the 4-point rule, which is what I'm gonna define on the next slide. Okay. So before we do that, are there any questions on this?
Is it the dx dy or it's not dxy, right?
Oh yeah, it's dx,
Okay.
dx dy. Thank you.
Thanks.
All right. Any other questions on this? Okay. And so let's go kind of one step up for this Gauss quadrature and discuss the 4-point rule. Okay. Oh, so there's a question. So why do we multiply by 4? And so this 4 right here, this 4 corresponds to the weights. Okay. And so depending on the rule, you know, you have to specify a certain weight to each of the sums. And so just for the 1-point rule, you know, if we go through the derivation, you'll see that the weight for a 1-point rule is 4. But that's basically where it comes from. And so for the 4-point rule, what I'm going to tell you is basically the coordinates for each of the 4 points, and also the weights that you're going to assign for each of those locations as well. But to kind of you know, to kind of tell you where that 4 specifically comes from, you know, if you look at this integral right here, which is from -1 to 1, right? And so our square actually looks like this. Okay? And so, you know, if you're integrating from -1 to 1, then the length of this side is 2, and the length of that side is 2 as well. Okay. And so the reason we multiply by 4 is that, let's say that our f, or our function of x and y, is just going to be 1 in this case. So it's just going to be a constant. Okay. And so we're going to integrate basically just 1 from -1 to 1 and -1 to 1. And so the reason we have 4 there is, you know, if we compute the area of the square, you know, we see that it has to be 4. And so that 4 is basically just to ensure that if we integrate basically a constant term, we simply get the area of the triangle out of it. Yeah. Okay. And so let's do the 4-point rule now. Okay. And so the 4-point rule has the following coordinates. Okay. And so I'm going to do this in table form. Okay. So these are going to be your 4 coordinates. And so I'm going to have one column for xi, another column for yi, and then wi. Okay. Okay. And so xi for this one's going to be -1 over √3. Be -1 over √3. Okay. This is going to be 1 over √3. And then -1 over √3. Okay. 1 over √3. 1 over √3, and then -1 over √3, and then 1 over √3. Okay. And then the weights for all of these guys are actually just going to be 1. Okay. Okay. And so if we evaluate this, then we get the following, if we use these rules, we get the following. Okay. And so our integral from -1 to 1 of f of x and y dx dy is going to be equal to f at the first Gauss point, so it's going to be -1 over √3, comma -1 over √3, with a weight of 1 out in front. Okay. Then we have f at the second Gauss point, and so this is going to be f at 1 over √3, comma -1 over √3. Okay. Plus f at 1 over √3, comma 1 over √3, plus f at -1 over √3 and 1 over √3. Okay. And so this is our 4-point Gauss rule. Okay. Okay. And so after this, I'm going to do just a quick example just to show you how it's done. Okay. But before we do that, are there any questions on this? Okay. Okay, and so let's evaluate this integral. Let's take the integral of from -1 to 1 and -1 to 1. of x squared y plus 3 dx dy. Okay. Okay. And just so that we can check our work, let's compute the exact integral. Or I'll do it and I'll just tell you the answer. Okay. And so the exact value for this integral is going to be 12. Okay. And so you can kind of verify that yourself. But let's evaluate the same integral using Gauss Quadrature. Okay. And so first, let's identify our f. Okay. And so our f of x and y is going to be just x squared y plus 3. Okay. And so now let's evaluate this f at each of the Gauss points. Okay. And so first we have f of x1, y1. And so this is going to be minus 1 over root 3 squared times minus 1 over root 3 plus 3. Okay. And we have f of x2, y2. Okay. And so this is going to be positive 1 over root 3 squared, and then minus 1 over root 3 plus 3. Then we have f of x3 and comma y3. Okay. And so this is going to be 1 over root 3 squared times 1 over root 3, okay, plus 3. Right. And then finally we have f of x4, y4. Okay. And so this is going to be minus 1 over root 3 squared, 1 over root 3 plus 3. Okay. And so we add them together. And then what we get is 12. Okay. And so you can see here that in this case, since you know the maximum order of our integrand was only 2, we have x squared. Then the Gauss quadrature leads to an exact integral. Okay. And so this isn't always going to be the case, because remember, Gauss quadrature is an approximate method. So you know there will be some cases where you end up with the exact answer, but there's also going to be a lot of cases where it's going to be off. Okay. But the idea is that if you choose the Gauss points to be in these locations, then most of the time you're going to get a pretty close solution, unless your integrand is something really crazy, like with lots of exponentials and x raised to the 19th power or something like that. But for most tame functions, which is generally what we see in finite elements, 2-point Gauss quadrature rules is usually going to be plenty, and so that gives you all the accuracy that you're going to need. Okay. And the nice thing about Gauss quadrature too is that it's actually very easy and very convenient to program. Okay? Because Gauss quadrature kind of falls under the category of an algorithm that that the computations are not that hard. It's just really tedious to do, and lots of things to plug in. And if there's anything that a computer is really good at, it's doing things that are really tedious over and over again. Okay. Okay. Any questions on this example here? Okay. So Gauss quadrature is great. It's good. It's going to be something that you're going to use on your projects. But there's one very glaring issue. Okay. And the issue has to do with the fact that in order to use Gauss quadrature, our integration bounds have to be from -1 to 1. Okay. And so, when this happens, that's great. But for most cases, this is not going to happen. Okay. Especially for an arbitrary mesh, which is what we're going to be working with in the project. Right, and so what can we do in these situations? So we love the idea of Gauss quadrature because it's it's fairly accurate and it's fairly easy to implement, but we can only apply it when our integration bounds are like this. Okay? And so in these situations, what we could do is we can perform a change of coordinates or a change of variables. Okay? In order to get our integration bounds into this form. Okay, and this is going to be really useful too because for the For the rectangle that we went over earlier in the lecture today, that was only valid when our nodes were kind of right on top of each other and we formed a perfect rectangle. Okay, but if we had some kind of skewed rectangle like a trapezoid or something, that's not going to work. But with this next theory that we're going to go over, which is called isoparametric elements, we can actually do that. Okay. Okay, so let's move into the next set of lecture notes, which is isoparametric 2D finite elements. Okay, and so just like we mentioned previously, the struggle with doing 2D finite elements, and it gets even worse in 3D, is evaluating the integrals for the element stiffness matrix. Okay, and so computing integrals is a pain. Okay, and so what we want to do is to not work in what's called the physical space, but instead let's work in a what's called a parametric space. Okay? Okay, and so the situation kind of looks like this. So let's draw kind of an arbitrary, quadrilateral like this. Okay? So let's number the nodes. And so this is going to be our element in physical space. Okay. And so if you're working in like ANSYS or something, and you measure geometry, using like the measure that's in there, you're going to get a lot of elements that look like this. Okay. But these elements are difficult to work just because you have to perform lots of integrals. And so what we would rather do is perform an integral on something that looks nice like this. Okay. And so we can say that the coordinates here would be like -1, -1. This will be 1, -1, 1, 1, and then -1, 1. Okay. And so our origin would be kind of like here. And so this is known as the parametric space. And so what we have on the right here is this is desirable. This is what we want, because performing integrals and doing calculation here are going to be so much easier. Okay. But in order to do this, we have to basically perform a change of coordinates, or in other words, what's called a mapping. Okay. We have to have a mapping between the physical space and the parametric space. Okay. And so this is an extra step, and so we have to actually compute this mapping. And so that's going to be the subject for the lecture today and next Monday. But once we do that mapping, then and work in the parametric space, it's going to help us a ton. Okay. All right. So the question is, does this method only work if the domain is four-sided? Yeah, that's a great question. So for the majority of this theory, we're going to work on kind of this four-sided transformation, just because the theory kind of works out pretty well. And at the end of the lecture on Monday, we're going to go over how to apply this for a triangle, actually, which is 3 sides. And so it's going to be a little bit different because the shape function is going to be different, but a lot of the same ideas apply. Yeah. Yeah, that's a great question, though. So that's a big part of your project too. So we're going to go over carefully how to do the 4-node triangle, but a big struggle for the project is going to be how do you apply the same theory with a 3-node triangle. And so I'll give you kind of the basics of it at the end of lecture on Monday, but a lot of the implementation is going to be up to you guys. Yeah. All right. And so the next question is, are all the points preserved in the new space? Yes, that's very key too. And so one of the key features of this mapping is that every point in the physical space gets mapped to a unique point in the parametric space. And so another way to another way to say this mathematically is that we can say that the mapping is 1-to-1 and onto. Okay. Right. And so those are kind of the mathematical terms for this. But basically, what it means is that every point that you have in the physical space has to be mapped to some point over here. Right? So if you have a point like this, that gets mapped to like something right here, and a point right here that gets mapped something right there. Okay? And this mapping is unique. Okay? And so you can almost think of every point in the physical space has kind of a counterpart in the parametric space. So that's all it means. So it's just a kind of just a fancy math term for that. Okay. Oh yeah, linear algebra. That's probably where you guys heard this this term before. Yeah. Okay. Are there any questions on this? Okay. Okay. And so this approach actually has a lot of nice advantages. Okay. Even though it's an extra step, it's I'm definitely acknowledging that. Performing this mapping and doing the calculations associated with that, it does have some extra calculations, but in the long run, it's actually going to save you some work. Okay? And a lot of it has to do with these advantages. Okay? And so the first advantage is that when we work in this kind of parametric space, the shape functions are easy to form. Okay. The next thing is that continuity across elements is easily satisfied. Okay. And so as you go across different isoparametric elements, then you're gonna have a continuous solution. Okay. And the most important thing that will and it kind of goes along with step 1 is that it allows us to use Gauss Quadrature in 2D and 3D. Okay. And for like a 4-node rectangle, which we saw before, where we have pretty complicated element stiffness matrices, this is going to be huge. Okay. Okay. And so just because we're in the parametric space, we can still form our shape functions. Okay. And so first, let me write down what the interpolation function looks like. And so this goes for any quantity, but I'm going to write out the interpolation function for temperature T. Okay. Right. Okay. And so what I'm going to use for this, because we're changing between the physical space and the parametric space, I'm going to use a different set of variables for that. Okay. And so for the physical space, typically we use basically x and y. Okay. Because we have x, y coordinates. But in the parametric space, I'm going to use a xi, which is this thing that looks like a tornado, and an eta. Okay, and so when you see xi and eta, all that basically means is just the coordinates in the parametric space. Okay, and so t of xi and eta is going to be t1 n1 of xi and eta plus t2 n2 of xi and eta plus T3 and 3 of xi and eta plus T4 N4 of xi and eta. Okay. Okay. And so let's write out the shape function for this. Okay. And so N1 is going to be 1/4 1 minus xi 1 minus eta. Okay. N2 is going to be 1/4 1 plus xi, 1 minus eta. Okay. N3 is going to be 1/4, 1 plus xi, 1 plus eta. And then N4 is going to be 1/4, 1 minus xi, 1 plus eta. Okay. So those are our shape functions. Okay. If you compare these to the shape functions for kind of the general 4-node quadrilateral that we went over earlier in the lecture, you can see these are a lot simpler because, you know, since we know what the x and y coordinates are of each of the corner nodes, you know, we can have just a simple 1/4 out in front, and then we just have a product of two terms like that. Okay. Okay. And so another thing that we're going to need is the shape function derivatives, and so we can easily, you know, take the derivatives of these guys with respect to eta and xi. Okay. But I think I'll do that on the next page since I ran out of room here. Okay. So before I do that, are there any questions on this? Okay. Okay. Okay, so let's talk shape function derivatives. So we have partial n1, partial eta. And so this is going to be 1/4, 1 minus eta. We have partial n2, partial xi. And so this can be 1/4, 1 minus eta. And we have partial n3, partial xi. This can be 1/4, 1 plus eta. Okay. And then we have partial n4, partial xi, which is, oh, sorry, there's going to be minus 1/4 here. Okay. And it's going to be minus 1/4, 1 plus eta. Okay. All right, so those are all the derivatives with respect to xi. And so let's do the derivatives with respect to eta now. Okay. And so we have minus 1/4, 1 minus xi. Okay. Partial n2, partial eta is going to be minus 1/4, 1 plus xi. Okay. Partial n3, partial eta. And so this is going to be 1/4, 1 plus xi. And we have partial n4, partial eta to be 1/4, 1 minus xi. Okay. And so those are all our shape function derivatives. Okay. Okay. And so what we can do, you know, with these shape functions and shape function derivatives is we can form interpolation functions for basically any quantity that we want. Okay. And so one example for this is going to be our coordinates, actually. So we can basically form the relationship between, we can use the interpolation function to find the relationship or the mapping between the physical space and the parametric space. Okay. And so what I can do is I can basically write out the functions x and y in terms of the shape functions. Okay. And so we can say that x of xi and eta is going to be equal to x1 n1 plus x2 n2 plus x3 n3 plus x4 n4. Okay. where these x1, x2, x3, and x4, those are the actual physical coordinates of the nodes, okay? And so those are in the physical space. And what this mapping does is that it uses the shape functions to kind of put these in terms of eta and xi, okay? And we can do the same thing for y. So we say y at xi and eta is going to be y1, n1 plus x2, or y2, sorry, y2, n2 plus y3, n3 plus y4, n4. Okay. Right. And so this kind of gives us the first step for our mapping. Okay. And so we'll pick this up on Monday and to see how we can use this mapping to actually transform our integrals. Okay. Okay. Are there any final questions on this? Okay. So that's all we got time for. So it's 6:45. So I'll let you guys go. And so thank you everybody for tuning in. So definitely take a look at the project specs, when you get the chance, because it's, there's a lot of information in there. And then probably starting on Monday, that you guys can probably start the project there. Okay. All right. So thank you everyone for tuning in. Have a great weekend, and I'll see you next week.
Thank you, Professor.
Thank you. Zaham, did you have any more questions? Okay. So I'm going to end the call. I'll see you next week.